Noether's work on topology. Actually, I looked into the net for quite some time, searching and libraries for writings on Noether on topology. And it seems there are only two articles on Noether's contribution in topology. One is by Dieudonné, and another is by Sanders MacLean. In Journal of Pure and Applied Algebra. In the same volume. I think around 1955. So although she contributed tremendously, but there's a lack of, I think, account of that. Okay, so what was Noether's contribution? See, first let us recall that Betti numbers were discovered by Poincaré. So I understand there are some physicists among the audience, so let me try to explain what is a Betti number. Take first, for each integer b and n, given a manifold or some topological space X, given any n, given n, there is Bn of x is a positive integer. What is that? B0 of x counts the connected components. Number of connected components. For example, B0 of a point is 1, B0 of a line is 1, B0 of a plane is 1. But B0 of a union of 2 points is 2, or 2 lines, it is B0 is 2. B1 computes the first homology, which homology group B1x, which computes the obstruction of a kind of measure to the obstruction. Suppose you take a loop, some kind of quantitative version of how it can fail to be contractible. Given a loop in a plane, you can deform it to a point. But suppose I give you the circle and give this loop itself, then you cannot contract it, because only the circle is the topological space. In between there is nothing else, right? My space is this circle itself, nothing else, only the circle. And then I take the loop given by the circle, defined by the circle, then there is no way to contract it, because there is no intermediate thing. Similarly, suppose you take a torus. So for the circle there is one loop which you cannot, but in the torus you can see there are two quite different loops. One is this one, you cannot contract. On the other hand, you have this loop which you cannot contract. So B1 counts this obstruction. So B1, I'll give it now, instead of defining it, I'll give an example. B1 of circle is 1, B1 of a plane is 0, B1 of a torus is 2. Huh? B1 of, exactly, yes, absolutely. So this B1, this given a manifold, this number was known. It was discovery of Poincaré, the Betti numbers, what are called Betti numbers. Now, what was the contribution of Noether in this? What she did is, actually it was, in the previous lecture, it was mentioned that she, instead of solving problems, she took some question, solving directly, you took a question and cast it in the larger setup of much more general and abstract setup, and then from that the solution was much simpler, and also it gave much more ideas and applications, etc. So what Noether did is that, what I'll now bring it to, what Noether did is to build homology theory. Yes.
So what is Betti Numbers?
Yeah, some mathematician. It was named, Poincare named it after him. It was Poincare, yes?
Is there a generalization for any Betti number?
Yeah, for each n, yeah. Z greater than or equal to 0? Okay. So what was the connection? See, Noether developed what is called modern algebra, which by van der Waals, and what calls modern algebra was, as he points out in his book, that it was developed by Noether. And the crucial concept in that on our work was idea of modules and homomorphisms. So let me say a few words about modules and homomorphisms, and they'll come back to these Betti numbers. So you start with a ring. It is like you have addition. It is something with addition, plus, and multiplication. The addition is commutative. Multiplication need not be. And they are related by the standard way. A plus B times C is equal to A times C plus B times C. C times A plus B is equal to C times A plus C times B. So before, instead of saying all the definition, etc., let us give an example that will be clear. So simplest example, integers. You can add and multiply, but in this case multiplication is commutative. Then another example will be a more natural, more interesting example will be matrices, n cross n matrices. Which is a real coefficient. You can take other, you can keep coefficients, complex coefficients. Now, of course, addition is commutative, but you see multiplication is no longer commutative, right? A times B is not in general, B times A. Not in general. So this is, let us take this to keep this in examples in mind. One is commutative, another is non-commutative, the multiplication. Now let us take an example of or let us define what is module. So this is the definition of a ring and some examples. Let us take module. rings act on modules. Modules are something on which rings act. Modules have abelian groups. Abelian addition, which is commutative addition structure, which is called abelian group. Mine is 45 minutes, right? So it is counting wrongly. So yeah, okay. So I should stop at 15, right? Because I guess, yeah, because it is counting from 1 hour, right? This one, okay. Okay, so rings act on modules and modules are commutative addition structure. Now, these two are compatible, namely, suppose M1 plus M2 times A is equal to AM1 plus AM2. So this is the compatibility between the ring structure and this structure. Now anyway, for what are the examples for Z module? For this ring are just, you can easily see that it is just commutative group, abelian groups. Same thing else. Now let us take the matrices, n cross n matrices. The most important example of the module for the n cross s matrices is just Rn. The real coefficient is Rn. Because R is an abelian group by the standard addition structure and the matrices act on that. Now, Rn itself and Rn with this module structure, there's a big difference. You see, by this action, any non-zero element of Rn can be transformed to any element. Given you choose any non-zero element, it can be transferred to any other element by the action of this. So this is a very large action. So that now let me get back to these Betti numbers. Now what I'll now try to say what Noether did. I'll just try to introduce something called Simplicial. Homology. This was basically what was developed by Noether. Simplicial homology is as follows. You start with simplices, a simplex, n simplex. Is a x naught xn in Rn, so that xi's are between 0 and 1 and summation xi. This is delta n, usually denoted by this is n simplex. Now, what is the face of the simplex? What are the vertices? Vertices of the form 0, 0, 0, some ith position 1 and rest as 0. So there are n plus 1 vertices. It is like a tetrahedron or a triangle. In 2-dimensional, it is first I start with the 1-dimensional. 1-dimensional, it is the interval. So it has 2 vertices. In the 2-dimensional, it is the triangle. It has 3 vertices. And in this case, it is a solid triangle, 2-dimensional. In 3-dimensional, it is a tetrahedron. It has 4 vertices. So in n-dimensional, it has n plus 1 vertices. Face consists of convex combination of some vertices, some subset of vertices. Of a subset of so this is a bit a confusing terminology because face by me we don't mean that face of only the codimension one things. Any higher codimension is also allowed. But face by face is still a face. Namely, if you take the tetrahedron, of course, these are the combination of the 4 vertices. So now if I choose these 2 vertices, 1, 2 and 3, so this will give me this face. But then I can check these 2 also, 2 and 3 just, and then this will be the face will be this line, or this line, or this line. Or if I just choose one single vertex, so the vertex itself, only the vertex itself will be the face. One should remember that the face doesn't mean that it is just one dimensionless, it means all possible dimension, lower dimensional things. But it is a standard thing, that means a combination of the edges that you mean, the generalized faces, face of a face is allowed to be, is also. Now, this is the basic building block of topology. Now a simplicial complex roughly is a union of simplices of different dimensions says that usually it is better to put finite union of simplices such that intersection of 2 simplices say tau 1 and tau 2. If you take or if you take two simplices tau 1 and tau 2 and they intersect, is a phase in both tau 1 and tau 2. And you represent topological spaces as a simplicial complex with the standard topology. So this is important condition that intersection of two simplices has to be a phase. For example, take for example the circle. Suppose I want to write it as a simplicial complex. So suppose I can write it as a, this is a line, half line. So this is a simplex, this is same as this, right? I can just straighten it out. So topologically, this upper part is interval. So this is a simplex, one simplex, and the lower part, the closed interval. So this lower part, there is also an interval. So that's also simplex. But the problem is that intersection is 2 points. So if it is a phase, then any combination of the points will be there in the phase. But if you take two combinations, then the entire line is there. So it cannot be a phase. It doesn't satisfy this condition. Combination of points in a phase. Phase is a convex combination of points of a subset of vertices. So if you take some point on the, so convex combination, if you take again further combination, convex combination of subsets, it still remain in that set, right? You have a set S, you take a convex combination.
Combination or subtraction?
Just summation, lambda I pi, summation is between 0 and 1, summation is 1, lambda I summation is 1. Yeah, 2 point is not a phase. Because it's not a simplex, because its intersection is, it doesn't correspond to some union or some vertices, because both the vertices there. So that means the entire line has to be there. No, with this decomposition cannot be composition. But you can do it as follows. Circle you can write it as, break it into 3 ways. So this is one simplex, this is another simplex, and this is another simplex. Now you would say intersection of any two is always a simplex, a phase, because these two will intersect only here and these two intersect only here. So you need to insert enough simplices to make it a simplicial decomposition. That's all I mean. Now, a simplicial decomposition of a topological space. Suppose I have a topological space. What is a topological space? I have a set with a topology on it. Topology means there is a collection of subsets which are declared to be open sets, such that finite intersections of open sets is open, arbitrary union of open sets is open, and the empty set is also open, and the full set is also open. And there are some, you can put some extra condition like Hausdorff, namely given to any 2 points there are 2 open sets, disjoint open sets containing the 2 points each containing the one of the points. And then you can, for most purposes, people take compactness, namely there are finitely many open, you can cover it by every covering of the space by open sets, there are only, you can choose finite of them which actually cover the space. So now, a triangulation means, a simplicial decomposition means you write it as find a simplicial complex such that it is homeomorphic to that. And fix a homeomorphism, right? Write it as topological space as a simplicial complex. These are examples of topological space. simplicial complex. And now I consider all topological spaces that are like this. Now this looks like a rather restrictive notion for topology, but this is not. For example, any manifold can be written as a simplicial complex. Much more general object. Every singular variety can be written as a simplicial complex. So now, I'll define, suppose C is a simplicial complex. Now I define Ck to be the subset, to be the union of K complexes of dimension K, simplices of dimension K. No, consider the union of simplices of dimension K and define Ck to be, let us call it Sk, Ck to be all formal sums, summation Ai, Ci, finite sum, such that Ai are in integers and Ci are in Sk. And it's a finite sum in the sense that Ai is equal to 0 for all but finitely many. So you take this is a formal sum. So you take all k simplices and take the formal sum with the coefficients, integer coefficient, call that Ck. Okay, I forgot to say something. In a simplex, one has to fix an orientation. Orientation by definition is an ordering of the vertices. For example, if I write it this way, it comes with a obvious ordering, right? 0, 1, 2. These are the vertices. Sorry, vertices are 1 in the ith place. So and rest are 0. So according to I going to 0 up to n, this gives the ordering of the vertices. So, but when you write it as a simplicial, decompose. So you have the in the simplicial decomposition, you have to also order the vertices, fix an order of the vertices. So that is called fixing an orientation. So I take a simplicial complex which is oriented. All simplexes are oriented, namely ordering of vertices. Now I define an operator del k from Ck. I have already defined what is Ck, the formal sum with integer coefficients of the element of the formal sum of simplices of dimension k. So Ck to Ck minus 1. So I have to define just delta, since it's a formal sum and it's a linear map, so I have to just delta k of sigma. This is summation I from 0 to k minus 1 to the power I. If the vertices are V1, V2, Vn are Vn, V0, V1, V2, Vk are the vertices of sigma, I just omit the Vi. So when you take when you forget the one of the vertices and take the convex linear combination of the rest of them, you get another simplex, lower dimensional. So given a simplex, its boundary is the boundary homomorphism. Its boundary is this, but you see here the ordering is used because ordering of the vertices is used because of this coefficient minus 1 to the power I. So now also note that the ordering depends only up to parity. Namely, it is if you make a even permutation of the orders, then this doesn't change. So this is only depends on the parity of the even or oddness. It is not exactly you have to actually order the vertices. You have to order the vertices up to a parity. Okay, now we are almost done, reached the definition. Now, Zk defined to be the kernel of and Bk is in Ck, contained in Ck, and Bk is the image of delta k plus 1. This again is contained in Ck. There are two objects you have. Next, because of this choice of this sign, appropriately chosen sign, it happens that delta k composed with delta k minus 1 is 0. If you compose twice, this operator is idempotent. If you compose twice, it becomes 0. No. No, it will, instead of integers, it will still be true if you have an abelian group. You need, you need an abelian group. Yeah, you can still make it. So that implies Bk is contained in Zk. These are the ones which have been obtained by applying the boundary operator once. So if you apply once more, since composition is 0, they are in the kernel. Image of this is in delta k plus 1 is in the kernel of delta. This. Now, homology, kth homology of this simplicial complex C is defined to be the group Zk quotiented by Bk. This is an abelian group. Everything is an abelian group here because I could have put it slightly more general coefficient, but let me just stick with Z coefficient. This is abelian group. This is abelian group. The quotient is an abelian group. This is defined to be the kth homology. Zk was the kernel. That means those which go to 0.
So what is the?
Huh? All those formal sums which go to 0. Just a second. What is the question? Let him hear.
No, CK is like one specific formal sum or
all possible formal sums. Formal sums which go to 0. Yes, Ck is all formal. This is all possible formal sums which the coefficients are k-dimensional simplices. Sk is the union of just the collection of all k-dimensional simplices. Ck is the all formal sums. All formal. Ck is, good point. I should have put bracket like this. Ck, you're right. This is. This is the bracket was missing. Yeah. Now CK is all formal sum.
So then you're considering the subset that whose boundary is
0.
that's BK.
Hmm.
That is BK.
And that is CK. And BK is the all those which are boundary of higher dimension. Yeah, sorry, I should have, this was confusing. I just wrote, I didn't put the bracket. These are all possible formal sum. Yeah. So now, when the composition of of the boundary of a boundary is 0. That's the.
The boundary of BK will be 0. Boundary of all elements in BK will be 0.
That means BK is contained in ZK. Because these are all which are boundary 0.
Some whatever.
Yeah. So quotient is the homology. And now, what happens is that Betti numbers BK of this corresponding topological space, which I also denote by C. I started with a topological space. I worked with a simplicial complex here, but I could have started with a topological space and write it as a simplicial complex. So now, here is, let me say one thing at a time. I start with a simplicial complex and I get this. Now I start with any topological space with whose simplicial composition is breakup is C. And it happens that the Betti number of that topological space, so that's called C. Topological space whose decomposition is C. BK of TC is rank of this. HK is a group. This is a group. These both are abelian group and a subgroup. So it's a quotient group. It's a quotient abelian group. Yeah, rank is basically the whatever is, but there's a group. There's no dimension. You take the free part. You forget the torsion parts. Finite term, order elements. You just forget it. Then it becomes a. It is like ZK. Z directs some K copies. So that K you call the rank. But it is all finitely generated, so I don't have to say infinitely generated group. Huh?
So the number of elements.
Number of generators. No, take the integers Z copy, direct sum K copies. Rank of this is K. Now, if I given a group, I can just quotient, forget the torsion parts. Those are finite. Those I can forget the torsion part, that's the free part, and that is isomorphic to this. And so then I call that K the rank.
Each element of the each K is like one of those groups.
Exactly. Yes. Yes.
So why isn't that a 0? Shouldn't that be a 0 element which is not a group?
Yes. Quotient. This every group has 0 element.
But for K, let's say for K equals 1, which is about group.
Yeah.
For K equals 1,
It's a constant loop.
but why is K equals 0 as a constant?
No, the loop means doesn't have is a map from the circle to the space. So it might be a constant map.
So my question is, what is H1 of a torus? What is H1 of a torus?
Is Z direct sum Z?
How many elements does it have? H1 of a torus.
It has 2 generators. It has infinitely many elements, but 2 generators. One is this circle, another is this circle. These 2 generate. Anything is a combination of these. There are of course many. I can take some of these 2. I mean, m times this loop and n times that loop. These are the generators. So what is happening? First, there was the Betti numbers. Given a manifold or a topological space, there is a notion of Betti numbers, which are integers, and then came the simplicial homology. Namely, you construct a complex. These are called complex. The CK. This is called CK. This CK minus 2. This sequence, infinite sequence. This is called a complex. Del K minus. you get a complex and the operator such that its composition is 0, then you take image by kernel and then you call the homology. So what has been achieved by this? What extra has been achieved? What extra has been achieved is tremendous. First of all, I mean, this became a part of a vast general theory. It is not something counting some numbers or something which Betti numbers were, but it became a beginning of a story by itself. This homology theory, homology and cohomology theory. I mean, its importance in mathematics cannot be overstated. Anyway, so now, what I want now let me give you some examples. Because it's kind of philosophical to say that it's much vast, general, much more useful, and etc. etc. Gives many theories. Unless I give you some example, what is the difference? Take for example, take for example the real projective space, RP2. You are familiar with RP2, right? So that means you take the sphere, you identify the two opposite points, antipodal points. That is called RP2. Now, if you try to look at homology group, so if you these 2 points are identified, right? Antipodal points are identified, right? Now take this. Just from here, this becomes a loop, right? From here you come up to this opposite point. In this RP2, my picture is wrong. I should do it more. It doesn't give the impression of a two-dimensional. Opposite points are identified. Now I take this part, only from here to here, this circle, right? The thickened part. I don't complete it, I just this. But this becomes a loop, right? Because these 2 points are identified. But this cannot be contracted. You cannot move and around. But on the other hand, if you repeat it twice, this, and if you do it again, then it becomes this circle, right? But this is, I can contract it in S2 itself. The problem of the first one is that what is the argument? The first one is not contractible because this is not a loop in S2. I have the ends are tied. I cannot move the ends. If I can move it, it has to be always on the antipodal. So there's no way to make it a point. But now, if I repeat it, then it becomes actual loop in sphere, and so then I can contract it. So this is the first homology. Each one of these RP2 is Z mod 2. This is related to the fact that very much, I mean, in physics you can, I think even physicists also have to see it many times, that fundamental group of SO3, that orthogonal group is Z mod 2. This is exactly that happens. Huh? Z mod 2Z. The a B1 or a pi 1 of the SO3 is Z mod 2, yes? RP2 is sphere identified with the opposite points. No, it is also called projective space. Huh? Yeah, set up line. Yeah, that yeah, you can set up lines in the. But real projective space in may mean different things. In algebraic geometry, it means I don't want to confuse. It is just sphere with opposite point. It is equivalence class of lines passing through the lines in R3. Yeah, lines in R3. This is lines in parameterizes lines in R3. Basically, if there's none, because it is a torsion group. If you try to compute Betti numbers, Betti number is 0. There's no, you cannot see any Betti number. Huh? Group is non-trivial. It's Z mod 2. But Betti number is you take the free part and then define its rank. But there's no free part. Free part is 0. So this I want, my time is actually, so now, what does it achieve? First of all, let me say what is process now. It has a now name for it. It's called categorification. See, I probably physicists are also familiar with that. For example, say Casson invariant, and say see, Casson invariant is of a three manifold is a number, but it can be written as a homology of the. So that is categorification. But for example, other not invariants or various things, when you have a just single number, instead of trying to understand the number as a homology of some complex, dimension of homology of some complex. For example, I should just, Casson invariant of a three manifold, oriented three manifold. Is a number, integer, is an integer. It is the intersection of the Lagrangian hyperspaces in the subspaces in the represented space of natural simplicity structure. You take the Lagrangians coming from this handle body decomposition and take the intersection and that count with multiplicity. That's how you get the Casson invariant. Now then, Floor defines a homology theory for the three manifold. Floor homology is called. And when you take the Euler characteristic, it becomes a Casson invariant. A floor homology is Casson invariant. So there are many other examples, important examples which has come up, even work coming out recently, on various not invariants, for example, categorification of not invariants. That's a subject by itself. So what Noether did was categorification of Betti numbers. Betti numbers were just invariants, some integer invariant. She understood them as dimension of homology of some naturally associated complex to the topological space. I think I'll stop here. Thank you. I wanted to say something because you can I thought I'll say some more about the homology and cohomology theory. That's why, but I ran out.